We're going to do Gaussian Discriminant Analysis. And also start talking about PCA. And then next week is the ethics module, which is a little bit more discussion-based. For half the time, there will be another teaching professor here, who will guide us through some discussion-based questions regarding, I guess, the ethics of recommendation systems. So you should plan to be in class tomorrow because there's also like a follow-up survey to the ethics module. That's also part of this larger CS ethics effort. So next week is the ethics module. And the final week, 2 weeks from today, we'll talk about k-means a little bit, which is an unsupervised learning algorithm. And I guess we have some flexibility on the final topic we choose to cover. So we can either discuss the EM algorithm, which sort of builds on k-means. It talks about how you can build a mixture of Gaussians. Or we could do some discussion on reinforcement learning. So reinforcement learning is sort of like a different paradigm of learning. We can go over some of the basics of how that works. So just as a quick straw poll right now, we'll put up a more formal poll later. Who thinks right now that they would prefer to learn a bit about the EM algorithm? Okay, and how about reinforcement learning? Okay, yeah. I think we'll probably go with RL, but we'll release the lecture notes from the past on EM if you wanted to look at those later. And then the final date should be set. I think it's April 14th in the morning. So that's a few weeks out afterwards. In terms of assignments, we're marking homework 2 and then homework 3 and the project are both out as well. Okay. Any logistical questions? Sorry, for the project, do you need the matrix factorization stuff? Oh, yeah, I guess today we'll also talk about matrix factorization a bit as an application of PCA and like how you would approach it independently. Yeah. So today we're also doing matrix factorization. Yeah, anything else? Yeah.
If we don't cover EM, would it still be on the final?
No, I don't think so. I think the last week the questions will be like 1 or 2 minor questions on the final. It won't be like the emphasis. Like the bulk of the stuff that is probably neural networks and then the stuff we cover this week and all the previous stuff building up to neural nets. Yeah, I think homework 1, you should probably just submit a regrade request if it seems the TAs didn't mark one of the questions, and then we'll get it fixed. I think the main issue was because we had 2 different platforms, the merging of the 2 grades got a little bit confused as well. So we'll fix all that. Okay, so just to recap what we were talking about last time, we were talking about linear regression as a maximum likelihood problem. So this sort of gave a more probabilistic motivation for how linear regression worked. And the way we did this was we assumed we were given a data set of a bunch of training examples. So we have x sub I, y sub I, maybe I equals 1 to n. And under this data set, we assume the data set comes from some noisy model. So each of the data points, yi, or I guess t sub I, is generated from a Gaussian distribution with some fixed variance. So this is the underlying noise model we assume for linear regression. And then we work through the derivation for writing down the likelihood of the data points. So how likely is each yi given the x sub i's? And then the parameters mu and sigma. So I guess the resulting expression basically we're trying to find like what is this linear model that maps you into this mean of the Gaussian distribution. So we wrote down the likelihood, and you take the log, and eventually you find, if you just look at the blue writing, you find that this is actually exactly equal to the least squares objective. So this is like a nice probabilistic interpretation that says if your data is coming from this linear model that has some noise to it, then to actually maximize the likelihood of the data you observed, what you want to do is minimize the least squares problem. So I can write that down to be more clear. So maximizing likelihood under Gaussian model. So this is like a more concrete motivations for why we chose to focus on linear regression for quite a bit previously. So that's the first step. And then the second step is all the writing in the red, which says there's probably also some uncertainty over the weights W. Like we don't know whether the weights W are some fixed value or like under some distribution. And if we assumed that the weights also come from a Gaussian distribution, so if the distribution of the weights also behaved like a Gaussian centered around 0, assume this is symmetric, then we can add this also to our log likelihood term, because we have instead the map estimate has two terms. We have the likelihood of the data given the parameters, and we also have some prior distribution over the parameters themselves. Then your total expression becomes, you add that term up top over there, which is proportional to E to some negative C W norm squared. And then when you go through the same derivation again to compute the log likelihoods, what you end up finding is you also have this additional regularization term. So this is a connection between regularization and this Bayesian sort of map framing. So it's saying that if there's some noise over your initial parameters, specifically Gaussian noise, that corresponds to minimizing the least squares objective in addition to a regularization penalty on your prior. So that's sort of the more probabilistic framing for the least squares and the regularization stuff we did before. And I guess we primarily did the univariate case here, but if you were to handle the more general multivariate case, you get very similar expressions. You just end up having to deal with matrices instead of just normal vectors. But the overall intuition still holds. Okay, any questions on this overall like revisit of linear regression under the probabilistic framework?
Almost something about the slides a little bit, but so for this slide, it's not using MLE, but it's using map.
Yeah, so I guess the MLE is just focusing on this first term. And then we can optionally also look at map, which is both of these terms. So map was like maximizing the posterior probability, which combines both the prior probability and also the likelihood of the data. So if you, I guess, if you max the posterior here, this corresponds to adding regularization to your least squares problem. Good question. I think we can write this out in a note a bit later and just post a PDF of the derivation again, so it's a bit cleaner and you can go through it again if you want. Okay. Any other questions here? Okay. Cool. So sort of the final part of this lecture is talking about Gaussian discriminant analysis, which is the high-level idea is we build a Gaussian model of each of the classes that we're trying to consider. And then for any new point, we try to find which class it belongs to by looking at the probability under each of our models that we've built. Yeah, so the motivating example, remember from before, is if you have some data, this could be really any data that's distributed along multiple different axes. We're going to try to form a Gaussian model for each of the classes and then find the probability of a new point under each of these Gaussian models. So the difference between this new generative approach is that rather than just trying to find the decision boundary directly, we sort of take two steps. The first step is we find the distribution for a given class, and then we apply Bayes' rule to get the actual probability a new point is in a specific class. So throughout this, we'll actually focus on binary classification, just because the math is a little bit cleaner. But in general, if you're trying to tackle multiple different classes, like if you have 10 different classes, you could do the maximum probability of t given x. So you just take the max over all t. And you can compute this probability for each of the classes and take the max over all of them. The binary case is a little bit nicer because probabilities add up to 1, so the threshold is sort of just set to 1/2. Okay, so the most general form, if you're trying to model the underlying distribution as a multivariate Gaussian, is you deal with this big equation here. So the probability of a given x in a class is whatever you get after feeding x into this equation. So this outputs a real number corresponding to the probability. And I guess each of these terms is roughly analogous to the 1D case. So if you look at this giant expression, it's a little bit intimidating, but I guess the key things to remember is this is a normalizing constant. So it just makes sure everything integrates to 1. And then this is a quadratic form. So it's a quadratic expression in terms of x's, and then we sort of saw before how you can draw the contour plot, like what the distribution actually looks like for a given covariance matrix. So sort of like how in the univariate case, you have to divide by 2 sigma squared. In this multivariate case, we have to consider this inverse of the covariance matrix, and we also have the 1/2 in front. So depending on how the covariance matrix is shaped, you'll get various shapes for your Gaussian distribution. Yeah.
So how does this, I don't know if I'm asking this a little bit too early, but how does this differ from k nearest neighbors?
I guess k nearest neighbors, we're just looking at the closest set of neighbors, which could be from various different classes. Essentially, yeah, we'll go through the procedure of how we do this, and I think it should be more clear why this is different. Yeah.
Is it set up like this because the SVD and the SVD math just makes it easier to actually calculate the number?
What do you mean, like how it's set up like this versus?
Like this equation.
Yeah.
Is it just because I'm struggling to see how you went from like having a matrix or an inverse matrix to a single real number. Or is it going to be a real matrix?
Yeah, it's actually just going to be a single real number because I guess the thing we sort of talked about the quadratic forms from before, but if you had an x transpose ax, that's mapping from Rn, which is like the dimension of your data. I guess data will refer mostly as R to the D for d-dimensional data, and this maps it to a single real number. You can, I think towards the end of one of the lectures, we talked about how you can draw the contours of this based on like a small example. In general, the contours are aligned with the eigenvalues of the A matrix. Yeah, I think Yeah, we'll make a problem on tutorial so we can work through them, like concretely how the eigenvectors, eigenvalues work too. Okay, so the expression in the exponent gives you a single number. If you exponentiate it, it's also a single number. And the normalizing constant, I guess the thing to note here is this absolute value bar notation around the sigma k denotes the determinant of the matrix. So if you model your problem in this way, for each class k, you end up having a mean vector mu k and a covariance matrix sigma k. So this is a d-dimensional vector corresponding to the mean of all the points you've seen in class 1. So I guess we can think of class 1, for instance, as spam emails, and class 2 as non-spam emails. And then the covariance matrix is a d by d matrix corresponding to the variances and covariances between each of the features for that given class. So one problem potentially with this sort of approach is we have a lot of parameters that we have to learn. In general, if we have k different classes, we're going to learn d times k total parameters for the mean vectors, and then d squared times k parameters for the covariance matrices. Okay, so let's talk about how you actually compute the maximum likelihood estimates. We aren't going to actually derive the formulas. I guess the formulas are pretty intuitive, and you can just more or less remember them. So this phi matrix represents the prior probability. And we calculate it as the number of observations of a given class over the total number of examples. So if we were doing spam versus not spam, it'd be like number of spam emails over number of total emails. We're using this indicator notation at the bottom, r superscript I sub k, to denote the ith example and which class it's part of. So it's going to be a 1 if it's part of class k, and 0 otherwise. So the way you estimate the mean vector using maximum likelihood is you take the mean of all the examples in the class. So if we focus on just spam emails, like we're trying to model the Gaussian for a spam email. To compute the mean vector, we average feature vectors for all spam emails. And then the covariance matrix, it looks a little bit more complicated, but I guess it's the same as how you estimate a covariance more generally. We're subtracting out the mean and then summing up the outer product of a bunch of different matrices. So this is the sum of outer products. And I guess we sort of interpreted what each entry of the covariance matrix looked like before. So this is like a very mechanical process. If you have all your data points, you can just group your data points by class, and then you can do np.average, or sorry, np.mean to compute the mean of all your points. And then there's like a covariance function in NumPy as well. Yeah, question up there?
So for the covariance matrix, is it the same for all clusters?
Right, so the first step, we're assuming we find a covariance matrix for each of the clusters separately. So there's a one covariance matrix for spam emails and one for non-spam emails. In some cases, you can make a different assumption, which is the covariance matrices are equal, and then we'll see how that leads to a different decision boundary as well. Yep.
So in practice, because like you said, there are so many parameters here. Like it's in terms of d squared.
Mhm.
So, in practice, would people, before doing this, would people like put a few convolution layers in the front to shrink the amount of size?
Oh yeah. I guess it depends on the task you're focusing on, right? Because I guess if you're working on spam versus not spam, convolutions don't make as much sense. But we'll see, like, we'll cover how PCA works later, and PCA is a dimensionality reduction technique, which you can often apply to reduce the dimension of your
So,
problem.
what's PCA?
Principal component analysis. Yeah, we'll talk about it later on in this lecture. But yeah, sometimes you do want to reduce the dimensions first before feeding it into your problem. Yeah.
So what's the advantage of having different covariance matrix for the clusters? Because I've read a couple of research papers,
Mm-hmm.
and all of them, they use the same covariance matrix for all.
Yeah. I guess, like, if you think the Gaussians for the two classes are distributed a bit differently, then it makes sense to use different covariance matrices, right? So for instance, if our sample data let's say this was one class and then the other class was just more clustered around like that, then it sort of makes sense to have different covariance matrices which sort of model the shape or the spread of the distribution rather than the same covariance matrix for both classes. Yeah. So in general, it's hard to picture high dimensional data as well, but we'll talk about how you can reduce the dimensionality of your data as well. Yeah.
I just making sure this, like the O versus the dash in the middle, that's prior, right?
Yeah, that's a prior probability for that class.
And what is R?
R is an indicator variable that becomes 1 if it's that particular class. So I guess in this case, we actually should have a phi subscript 1, which is like the prior probability for class 1.
So like Ri would be 1 if data is in class I.
Ri would equal 1 if it's in class 1.
Right.
Ri subscript 1, yeah, I guess. The notation's a bit more confusing than it needs to be. Like the intuitive way to think about it is the right way. Like it's just however many spam emails you have, that's your proportion. That's your estimate for the prior probability of the number of spam emails.
So R superscript I is equal to 1 if it is class 1.
Yeah, exactly. Yeah. And in general, if it's K, it's like whenever it's class K, it's equal to 1. Yeah. Okay. So in general, for decision rules, we have to use Bayes' rule to figure out the actual probability after you see the data point. And we use Bayes' rule to simplify this expression. So P of t is the prior probability. And then here, P of x given t, we're using this multivariate Gaussian that we just formed. So we know the mean and the covariance of the multivariate Gaussian, and we can plug it into P of x given t. And in general, we're just trying to find the probability of the, like whichever class maximizes the probability. So we don't have to worry so much about normalizing because the denominator is the same across every class. Okay. So basically, once you compute the quantities above, you can just go ahead and apply Bayes' rule, figure out what your decision boundaries look like. And it's easier to work with log probabilities. Like remember, log is a monotonic function, so we can apply log to this entire expression. And basically, it's going to decompose into a bunch of different terms. The exponent pops goes away because log and the exponent cancel, so you're left with this term here, and then some other terms that are more constant. So you can do this for every class you're considering. In general, our decision boundary is going to be where the probabilities are equal, right? So we want to find where log probability of T1 given x is equal to log probability of T2 given x. That's where, that's the decision boundary where you make classification of one class spam on one side and non-spam on the other side. And if you solve this expression, some of the terms cancel and you're left with mainly just the quadratic term, the quadratic form expressions. So in terms of a function of x, you have quadratic terms of x. So here, the mu's and the sigmas we've estimated, they're just vectors and matrices of numbers. And overall, this is like a quadratic function of x and some constant term. So most generally, the decision boundary is actually something called a conic section because I guess that's a functional form of a conic section. In general, it's actually usually going to be just some sort of curved looking shape. So here's a visualization of if you had two different underlying data distributions, you would estimate the mean and covariance of each one and then plot where the probability equals a half. It's going to correspond to some curved decision boundary between the two data points. Okay. So one other simplifying assumption that we often make is we assume the covariance matrix is shaped the same across all different classes. And that ends up simplifying the equations quite a bit because if the sigma inverses are the same, you can move them to the same side. And this just becomes a linear function of x. So under the assumption that each class has the same covariance matrix, we end up with a linear decision boundary. Here you can, I guess here's a picture of what a linear decision boundary looks like if you assume the same covariance matrix. And one natural point of comparison here is we previously looked at how you go ahead and cluster two different classes using just directly the discriminative approach, which is logistic regression. And you sort of want to compare how this linear decision boundary looks compared to the one found by logistic regression. And, sorry, this cable is a little unstable today. Okay. Basically, there's a main trade-off here is the Gaussian Discriminant Analysis approach makes a stronger modeling assumption, and that it assumes the underlying data comes from a Gaussian itself. Whereas the logistic classifier tries to find the decision boundary directly, and it doesn't have this implicit modeling assumption. So I guess generally when the distributions are non-Gaussian, logistic regression usually beats Gaussian discriminant analysis. But Gaussian discriminant analysis can sometimes do better when you have missing features in some of the classes because it just sort of ignores that feature. Like logistic regression can't easily handle that case. So this can ignore features that don't, or ignore data points. Ignore features with missing data points. And we can draw out an example where you might expect logistic regression to perform better. So if we had two classes, blue and red, if one of the classes looked like lists and the other class was somewhere here, then logistic regression works really well on linearly separable data. So go ahead and just like find this decision boundary here. So logistic regression can find the decision boundary, but if you try to model the blue points with a multivariate Gaussian, that's sort of a tricky thing to do, right? Because the points sort of have two different modes, and it's going to try to interpolate between the two modes to capture the likelihood in both. So you might learn some distribution that's centered around the middle. Like the mean would be estimated to be somewhere between the two clusters. And I guess this has the net effect of potentially moving a line a bit closer to the blue points and not giving you a more natural distribution. So that's sort of like a hand-wavy intuition for why you might prefer logistic regression over this Gaussian approach. So under the Gaussian approach, Gaussian discriminant analysis, it's harder to estimate the mean when there's two different modes. But if the data is actually Gaussian, then this approach is the best thing that you can do.
Or when you're saying Gaussian has is hard to estimate, do you mean by like Gaussian has two lines, or is the line just not correct?
Yeah, I think you can construct the example in such a way that it might classify some of the points incorrectly. This is sort of more of a cartoon illustration, but you can definitely construct an example where logistic regression finds a decision boundary that separates the two classes, but this approach fails because the data isn't actually a Gaussian.
But Gaussian is hard to estimate the best value if it's
Yeah,
Gaussian.
yeah, when the data is non-Gaussian. Yeah, that's a good question. I guess you could try to visualize it in lower dimensions just to see if it's approximately looks like an ellipse, like the distribution of the data. There's probably statistical tests you can run to estimate how closely a data distribution actually follows a Gaussian. I guess the other empirical thing you could do is just try to run both of the algorithms and then see which one gives you better results with the validation set.
On your slide, like you were showing how like GDA works, there's something about the discriminant being 0.5.
Yeah.
What is that?
Oh, yeah. I guess basically because we're trying to find the decision boundary where the two things are equal to each other, if there are only two classes, you can also just set one of them equal to 1/2 or 0.5, and that should give you the same answer as setting the two probability expressions equal to each other. Okay. Yeah. And I think there's also a third assumption you could potentially make, but I think this one's a little less common because it's less likely to actually occur in practice. So you could actually assume each of the features are independent. I think we're deciding like you don't have to worry so much about this approach, but just know that it exists. And basically the end result is you'll end up finding isotropic, meaning the covariance matrix is the same in each of the dimensions. Okay, so the overall recap of generative models is if you do it naively with no additional assumptions, you'll have a quadratic decision boundary. If you have a shared covariance matrix, you end up reducing to a linear decision boundary with a similar function form to logistic regression. Yes, one potential advantage of linear versus quadratic is linear decision boundaries are probably less likely to overfit. And generative models have some approaches, like this is sort of the second lecture we're talking about them. They're flexible, easy to add or remove an additional class. Like if you have another type of classification you want to consider, such as maybe you want to separate emails into important and not important emails as well, then you can just build an additional model for that new classification. And it's really easy to add or remove classes because you just have a model for each of the classes. It's oftentimes easier to handle missing data as well, and then there's some like nice probabilistic interpretations you also have. But because you make this additional assumption of trying to model P of X, we oftentimes get harder. Like it oftentimes has the consequence of making the underlying problem a little bit harder too. Okay. Any questions here? Yeah.
If I talk a little bit more on why it handles missing data.
Yeah, so I guess, yeah, we talk about this a bit in the next part of the lecture as well, but if you have a feature where, let's say the values are like 7, 3, and then we're missing the value for 2 of the data points, and then we have a bunch of other values. If you're just trying to estimate the mean, it's very you can just average the values that you have, right? Or if you're estimating the covariance, you can just skip the ones that are blank for that particular covariance calculation. So like probability-wise, like the maximum likelihood estimation's reasonably well defined and under missing data features. Yeah, so just skip the ones that are missing. I guess another thing that's sort of of interest lately is if you consider a giant pre-trained model like ChatGPT, is it going to be discriminative or generative? Like which framework would we consider it under? Yeah.
Sorry, can you repeat what is this difference between descriptive and generative again?
Yeah. We'll just pop. Sorry, yeah, we have a slide over here. So generative tries to model the distribution of the underlying data, and then discriminative just tries to model the decision boundary directly. So I guess the underlying thing is you try to model P of X, where X is like the raw data points themselves. So what do we think like a big pre-trained transformer or neural network model might be? Yeah.
Probably generative.
Yeah, do you want to speculate on why?
It seems like it would be pretty hard to find decision boundaries in such like a broad class of data
Yeah.
that like ChatGPT could take in.
Yeah, that's right. So I guess last week GPT-4 just came out, which is sort of a more larger, potentially more capable model. But the high-level objective, this sort of relates to the next topic as well of unsupervised learning, is if you have a bunch of different words, so W1, W2, all the way to, let's say, WN, then the sort of the modeling loss that you have for training the unsupervised model is you want to maximize the probability that your model predicts probability of Wn given W1 through Wn minus 1. So the idea here is that you take in all the words in a sentence so far, and you're going to try to predict the probability of the next word. And then in this way, you basically learn a generative model, which is a model that understands the underlying distribution of words. So this is a model This is a model that tries to capture some underlying properties of the words themselves, and it's not really trying to classify things one way or the other. Okay, yeah, because we're a little bit ahead of the other lecture section, we can, I guess, do a quick GPT demo, since it's also machine learning relevant.